Today, the topic is mapping AI methods to tasks in traffic management. But first, I want to introduce a theorem in machine learning called no free lunch theorem. We'll have free lunch for today, but in machine learning, we have a saying that there is no best model across all problems and all data sets. So that's the no free lunch theorem. Having said that, it also tells you the objective of this lecture is not to teach you the best AI model for a traffic management task. It's impossible to do so because we have so many models available. But about showing you the way of thinking behind the choices of models. And first, I wanted you to participate in a pool. So if you scan the QR code or go to wevox.com and enter the session ID 156815148, you'll see the pool. The question is about what factors are important to consider when choosing AI models for traffic management. Let's see if we could see some emerging patterns from all the answers. Okay, so it's really happy for me to see that the top words popping up are robustness, reliability, explainability. This is a really fantastic news for someone passionate about explainable AI. But we can also see some other common themes, for example, complexity, real-time, reliability, performance, pricing even, accuracy, of course, data requirements, accessibility, computation time, scalability, AI knowledge, model size, prior knowledge, inference speed. Those are all fantastic aspects. So next, we're going to look in detail all those factors and how to choose your model based on each dimension. I hope this covered all the points that popped up in the survey. I classified them into 5 main points. Let's turn off the translation. Task, data, performance, infrastructure constraints, and also ecosystem integration. So we'll look into each one of those aspects in detail. First, task. Before we choose a model, it's important to understand what your final goal is, right? We also learned a little bit from yesterday. There are different types of machine learning models. You have unsupervised learning, you have supervised learning, you also have reinforcement learning, the general category. And those relate to different specific machine learning tasks. So if we want to do a prediction, meaning you have certain given data and you want to predict the unknown data items, we could use supervised machine learning. And if you want to do a classification, meaning you have a set of data and you want to allocate a label or a class or category to your data points, and then you would choose a classification type of model. We have supervised machine learning for discrete variables. And what if you don't know the classes, but you still want to group them? So that's a clustering problem. And for that, we have unsupervised machine learning. And we also have the task of anomaly detection, identifying abnormal patterns or incidents in the data. So for anomaly detection, both supervised or unsupervised machine learning provide certain methods to help us achieve the goal. And also generation. We talked briefly yesterday, generative AI methods learn the distribution of data. We need to create new data that are not present in the training data. Generation or generative models are one of the choices. And lastly, for control or optimization tasks, for example, traffic signal control, you would like to have an algorithm that helps you optimize your policy. So reinforcement learning is could be one of the candidates for that task. And now it's a question for you. Let's say you want to create a synthetic data set that simulates the collision of autonomous vehicles. And then the second step is you want to use those synthetic simulated data to help you train a controller to avoid the collision. What kind of tasks are those? We introduced the 6 tasks in the previous slide. For these 2 steps, which task do they belong to? Control? We have 2 steps. Which one is control?
Second one is control.
Yes, second one is control. How about the first one? Generating synthetic data that simulate the collision of autonomous vehicles. Generation task, yes. Very good. So next question. Let's say you have the historical traffic speed data per road segment sampled at a 15 minutes interval, and you want to know how the traffic speed will be in the next 1 hour. What kind of machine learning method should you use for this task? Is it supervised or unsupervised? Supervised, very good. And if you recall the general neural network architectures we introduced yesterday, considering the data type, what kind of models might be a good candidate for this type of tasks?
Recurrent.
Yes, recurrent neural network, because we are looking at a time series data, right? You want to be able to predict the future state based on the previous time steps. And I also wanted to give you an example. So for the same problem, we can also use graph neural networks because we have a spatial dependence and the road structure as well. So the example or the animation shown on this slide is a study published by Google DeepMind. They use graph neural network to predict the estimated travel time for road segment. So this animation nicely illustrates the process of converting a physical road network to a graph neural network. And an engineering technique particularly used in this study is segmenting a large road segment into small chunks. They call them super segment. And then each small super segment is denoted as a node. So now we attract the nodes, and this step is to learn the representation of the traffic state using a neural network, and this step is to aggregating the adjacent information to help you predict the current target location's traffic state. And that's about prediction tasks. So the second dimension I want to talk about is data. And a couple of aspects. One is data modality. Is that tabular data or image data or text data? Text data can be sequential data or video data. You have both spatial and temporal dimensions. And closely related to data modality, we have data structure. Is it image-based data? We talked about the general fundamental neural network architectures yesterday, and there is one designed particularly for image-based data. Anyone remembers? The one that has 2-dimensional weight filters. Yes, convolutional neural network. And also we have graph-based. We just introduced for graph-based data structure. It's suitable to use graph neural network. And also sequential data. Again, it's a recurrent neural network is usually a good candidate for it. When I say a good candidate, does that mean it will be the best model? It really depends on all the other dimensions we're going to talk about today. And the third one is data volume. So how big the data set is. We have, on one hand, the traditional machine learning model that's not so deep. And within the machine learning domain, we also have this branch of models that are called deep learning. Deep learning models are capable and powerful that can learn very minor and complex patterns within the data. But the disadvantage of many deep learning models is the computation intensity and also the complexity of the architecture. So when you have a large data volume, you have sufficient information to feed into a deep learning model, and it's worth using a deep learning model. But if you only have, let's say, hundreds of records, then it's not really worth the effort to utilize a deep learning model. And another important factor is label. I guess by now you would already know how that classifies two very important types of machine learning models. One is supervised machine learning. We have label to guide the learning process. And then the other one is unsupervised machine learning, where you do not have the label, and you're hoping to find pattern from the data. And lastly is data quality. Yesterday, some of the talks mentioned data quality in the traffic management domain. And in the AI field, we have models that are developed specifically to be more robust towards missing data or adversarial attacks or bad data quality. So if you already know that your data set has a lot of missing data, then considering the models trained specifically for accounting for that disadvantage would be one of the options. For example, tree-based models, that's a traditional machine learning model. If you use an ensemble tree, like a random forest, that's usually more robust compared to a simple decision tree. Because through the ensemble process, you have a lot of random sampling of data samples and also features. So that's already in the training process, and design of the algorithm accounts for missing data. Or in neural network architectures, now a lot of neural networks will have, during the training process, will have masked functionality to mask out certain input and train the neural network. So those neural networks are also more robust towards missing data points. And here I'm going to give you an example related to how the data aspect will influence the performance of and also the choice of the neural network architecture. The example I'm showing here is the traffic forecast competition hosted by IRI, Institute of Advanced Research in Artificial Intelligence. So they hosted this traffic forecast competition 3 years in a row. But surprisingly, 3 years in a row, the winning model is a UNet model. If you don't know what a UNet model is, no worries. So the architecture is shown on the right of the slide. The important thing to know about this UNet model is it has two major components, an encoder that compress the input data and extract the most essential information from the traffic video data. And then there's a second part, decoder, so the one from smaller becoming bigger blocks, to reconstruct the traffic video. So this model has really good performance in terms of compression data and also reconstructing the key information of data. But not everyone was expecting that compared to some other models that are designed particularly to capture temporal dependence, like recurrent neural networks or temporal autoencoders, this one performed better. Why is it? One of the key factors is the input data is image-based. So UNet has a convolutional filter, and it's really good at extracting the spatial information from the input data. So if it were a sequence-based data input, maybe the UNet model might not be the top one across the 3 years. But because of the input data format is image-based, it's really made model that have the convolutional filter stand out. So as you can see, the input tensor, I don't have the fancy highlight, but on the right side here, it's image-based. Each grid is 100 meter by 100 meter, and we have different features. For the dynamic feature, the input are traffic speed, traffic flow, and there are also some contextual features. For example, number of intersections and number of incidents associated with a specific grid.
Can I ask a question? How
Yeah, sure.
do you feed into the model the traffic congestion then?
Traffic congestion is considered as one of the contextual features. Actually, no, it's considered one of the dynamic features. I will later show a figure that shows the It's quantified as incident level by the data provider. In this case, is here. So they defined an interval from 1 to 10, and congestion or incident levels of 10, meaning higher congestion or higher incident levels. And then the lower in range means low congestion level or incident levels.
But how does it transform to an image or a grid?
It just assigns the value to the grid at each time step. So this is not just a static image, it's a pile of images. So every 5 minutes, sampled at 5 minutes interval, every 5 minutes you have a snapshot. And then you have a stack of images as input. This is a very interesting data set to play with, maybe useful for your group assignment. And they are also covering multiple cities. Next dimension we want to talk about is performance. Of course, that's our KPI. And what are the important KPIs to consider in traffic management? Number one, accuracy. So that's a base KPI to think about. And depending on the task, we can have different accuracy measures. For regression tasks, it's quantified or continuous target variables. The accuracy is measured by an error value. And for classification tasks, the accuracy is usually measured by precision or recall. Why the accuracy is important for you to choosing models? Because let's take a classification as an example. Precision means you want to have a fewer false positives, meaning all the ones recommended are more or less to be true. So recall means you want to have fewer false negatives, meaning you don't want to miss any possible instances. Let's take traffic incident detection as example. So if you want to have a high precision, you want the algorithm to tell you less alarms or less candidates of possible incidents. But among the choice of recommended incidents, they have a high confidence of being a real incident. So that's precision. But for recall, you do not want to miss any incident, possible incident. So you want a broader set of recommendations. You see that when you have a preference towards which metric you're looking at, that influence how you choose your models. Because some model will have a better performance in precision, and some model will have a better performance in recall. And the second one is speed. So certain applications will require that you have a very short response time and being able to continuously learn. So those are called online learning. Usually we'll employ online learning algorithms. And some you don't need to have very fast update speed or response speed. And for those, we could train the neural network or train the machine learning model offline. And then usually during the inference period is faster and deploy it after training. And the third aspect I want to talk about is scalability. So how easy to scale your model to a larger city or over a longer period. And some of the models are really simple to implement, but when you consider the scale of a road versus a region versus a city, country, global scale, that will dramatically change how well overall performance of model is. And explainability. A lot of the input from the early pool indicated that being able to explain or understand the outcome is very important for traffic management. That means for some cases, we might prefer the fact of being transparent over the fact of having the best accuracy or having the fastest speed. In that case, certain simple interpretable machine learning models might be a better candidate or choice compared to black box complicated deep learning models, like linear regression models. If it helps to achieve the goal and very reliable and also easy to explain, it's not necessarily to be a bad model in that specific situation. Of course, on the other hand, we want to utilize the superior prediction performance or computational power of deep learning models. So what we do nowadays is to add an explainable component to those black box models. So that's the active research field of explainable AI. And another aspect is robust. We train the model using data that are relatively clean. When we deploy the model in real world, there are so many situations could happen. Besides missing data, you could have cyber attacks or even have distribution shifts, meaning that your pattern has dramatically shifted compared to the pattern that you use for training your model. So we want the model to be able to account for all those different challenges. And lastly is uncertainty. Does your model need to output an uncertainty value? So does the stakeholder need to know the confidence level of the prediction? So that also limit or decides what kind of a model you should choose for your task. Let's again look at the traffic forecasting example. So besides the accuracy metric we looked at earlier, now we have additional requirement. We want to offer explanations on the contribution of each historical traffic state to the traffic prediction. Why it's important? Because in certain cases, maybe due to limitations of storage or computational resources, we don't want to have all the past 1 day of data as input. We just want to have as few data points as possible, but still achieve decent or sufficiently good prediction outcomes. So it's important for us to know which exactly the contribution is from the past historical data. And for achieve this, we did a study on using the explainable AI method because we have image-based input. So the method used here is gradient-based feature attribution. There are many different variants of the gradient-based feature attribution method. The basic fundamental idea is very simple. It's a bit like the back propagation algorithm we talked about yesterday. And now instead of back propagating errors, we back propagating the prediction values. Then we fix a target in the outcome or in the prediction. We calculate the gradient of the outcome with respect to the income, each pixel. And the weights now tells us how important each pixel is to our specific target prediction. When we aggregate those importance levels by different dimensions, for example, by the temporal dimension, the time step, we know the accumulated importance or contribution from that specific time step. When we aggregate the importance or contribution from a specific feature, and then we know the importance of that specific feature. So here is the results. As I mentioned earlier, for the input data, we have traffic speed, traffic volume, also the incident level as dynamic features. So those are all time series data, but in the image format. When we calculate the contribution of the 3 features in the past 1 hour, since it's sampled at 5 minutes interval, there are 12 steps, we see that the latest time step contributes the most to both traffic volume prediction on the left and traffic speed prediction on the right. And when including all the previous time steps, meaning the time step number 1 to 11, it only helps lower the mean squared error by 0.6%. So it's really marginal improvement when you considering all the previous 11 time steps. This result shows that for the UNet model, it mainly utilizes the latest time step. So if you are constrained with computational resources or the storage space, you could simply just use the past 5 minutes. That already gives you very good prediction outcomes compared to using the past 1 hour input. Next, since we're talking about constraints of computing resources, here I want to highlight another key dimension for choosing AI models, infrastructure constraints. So besides memory, we also have nowadays, if you want to run deep learning model or even large language model, a very important factor to think about is, does it need GPU or CPU is good enough? And also the latency tolerance. Do you need seconds of response or minutes? And another one is energy constraints. If you use edge computing, you probably want to make the algorithm lightweight, so to conserve energy. So those will all influence your model choices. And lastly, I want to talk about the ecosystem integration. What I mean is, in a traffic management application, it's usually not a standalone algorithm. You always wanted to plug your algorithm into a big, complicated system, right? So very important, you want to make sure that the input and output of the model, and also the platform that you use to host the model, needs to be compatible with the existing ITS infrastructure. And also, there are standards or requirements for employing certain models in a traffic management system. For example, large language model is showing really good generalization ability, also prediction ability in many applications. But because of the safety concerns, it is not allowed to be employed still in many applications nowadays. So be aware of those requirements or standards are essential for choosing the models. Now time for quizzes. Considering the 5 dimensions you just learned, we have task, data. What's the third one? Anyone remember? Performance and infrastructure constraints. Lastly, yes, ecosystem integration. So considering the 5 dimensions we just covered, I want you to pair with your classmates, maybe per table, and discuss this scenario. Let's say you want to identify abnormal hotspots of shared bicycles. For example, sudden surge or cluster of bicycles in a park. You are given certain conditions. One is there's no labels of anomalies or abnormal patterns. And you only have GPS points of the bicycle updated per minute. And there are thousands of bicycles for the entire city. And the requirement, you also need to make the prediction in a very low latency requirement. So have a prediction at the seconds level. And there is no edge compute in the scenario. And of course, the algorithm needs to be scalable to the entire city. So I'll give you 5 minutes to work with your classmates and think about what kind of models should you choose in this scenario. Good. So time up. Which group would like to share their solution? I see your group was still, actively discussing. Maybe wanted to share with the rest of the class?
So we were thinking, as the data is quite limited, so we have the unsupervised machine learning because we don't have labels. And we are also thinking maybe we can convert it to images and can use convolution maybe also.
Yeah, those are really good points. So number one is because of no labels, you would choose which one?
The unsupervised.
Unsupervised machine learning, yes. And it's possible to convert the points into images, and then you could use convolution to learn the patterns, spatial patterns. That's a very nice point.
To aggregate all the data that we receive every minute and create a sort of grid of data and then analyze that with CNN.
Yes, that's a really good point. So using the convolution filter, aggregate points into grids and analyzing the image patterns. That's one way. It's actually the methods shown on the example or sort of in that direction using image-based format. And also autoencoder, similar to the UNet structure we showed earlier, to detect the abnormal patterns. Other ideas or groups? People on this side?
Yeah. So I kind of saw it between anomaly detection or clustering. I thought, the clustering came to mind first, but then it kind of feels like it depends a bit on what exact inputs you want, maybe, because the clustering, I suppose, will find groups and find points where, like it would spot in that normal graph, it could spot
Yes.
the center, but then you need to know the next step of where do I need to have my attention on, and so I guess the anomaly detection is finding those specific peaks and would be able to point you more directly towards.
Yes, that's a really good process or solution as well. So decompose the problem into 2 steps. The first step, still treating them as point data. First step, doing clustering is an unsupervised machine learning method. And then during this clustering process, you might be able to find anomalies, like points that cannot be clustered easily with other bigger groups, or depending on how you want to quantify it, or peaks in the figure that can show you which one is anomaly. So 2-step clustering and then anomaly detection. Very good point. Other groups? We already covered cluster-based anomaly detection approach, and also image-based or reconstruction-based anomaly detection. Any other suggestions or ideas?
Or should be real time because they have GPS points or bicycles up in the minute.
Yes.
The algorithm should work real time, and also this is scalable to the university, so we also scalability.
Indeed. So being able to update the detection in near real time or real time, and also being able to scale will be important limitations or constraints for the model choice. That will translate to maybe the neural network structure would be how deep you want the neural network to be, and also that influence the training and the inference time, and whether you can bring that algorithm to online, meaning digest data streams rather than you have to digest the whole data set at the beginning. Other ideas, I'm still looking for, because we covered the clustering-based anomaly detection and neural network reconstruction-based. There are also like other main streams of approaches. What would you think of as anomaly in traditional statistical sense?
Outliers.
Exactly. Then outliers is always with regard to some sort of distribution, right? So we can also use the statistical-based models to model the normal distribution. I mean, not really normal distribution, but the distributions of normal patterns. And then the point that's lying outside of those distributions are considered as outliers. So that's another way of thinking to address this problem. Great. So last, the summary slide or checklist for you to choose AI models. So we covered the task dimension, prediction, classification or clustering, anomaly detection, generation, or control. And the data dimension, and also performance. Last 2 is more related to deployment of AI models, infrastructure constraints, and ecosystem integration. Last slide. I wanted to ask after learning all the 5 dimensions, what is your main takeaway from this lecture? I see you raise your hand. Is that for answering this question? Okay.
Yeah, something was very new and interesting for me because usually when they are talking about model performance, about precision or recall which one should we pick.
Yeah.
And I was good recap for me to remember that it really depends on the objective of the model. So why we are training this model? Because usually these performances are not saying the same thing. And usually there's a discussion, okay, then in what metrics is doing good and others not doing good. So what should we do? Should we go forward with the model or not? But it goes back to the objective of model. So why the model has been trained on. So it was a very good.
Very good. Thanks for sharing. Other points?
Yeah, I don't know all the machine learning models or AI models. Is there a kind of diagram where you can choose from on
Yes. So that's also the purpose of this lecture. With this slide, you could define your search term for Google or for ChatGPT. Every combination of those dimensions will give you a narrowed down list of models that can potentially help you address the specific problem. But once you have the list, does not mean all the models there are the best, but they point out the directions regarding the model structure, regarding how you do the data input integration, and also the output format. So those could be used as a seed for you to customize a model or even invent a model for your problem. Other takeaway messages or the things that you learn from this lecture that might be helpful for your own problems.
This overview of summary is very clear for me as a person now working directly with machine learning. So I can see the prediction method that I'm using, how it can be fitted into a machine learning field somehow.
I see.
If I want to go forward in machine learning field, what can I add to my current probabilistic method that I'm using?
Nice, thanks. Good. So that concludes today's lecture. I hope you all take something useful from this lecture.